All right, so here is classes in week 3. Labor Day kind of skewed things. I'm going to keep with my designations for the weeks, but we'll probably will always be shifted by 1/2 of a week. So we're going to deal with damped free vibrations and in this course. All right, so here's the section of the book that we're dealing with, and here are the suggested problems, including a problem set right there, and they should be posted on Blackboard. I encourage you to work through those. I believe I will have posted the solutions to these from the textbook, and if I can, I will write them out myself, so you'll see a slightly different approach and fully worked out. So we're in this topic here of damped free vibration, and it begs the question, what is damping? Maybe we already, from these pictures, we might already have some idea right here. I saw a definition that I liked right here, and I'm going to put it down, of energy absorption. Energy absorption. Absorption. Okay. Of course, that's we can say, or we can say dissipation. I guess you say dissipation. If we didn't have damping, we would have a signal and it would continue forever, right? But we know that there exists some amount of energy losses that are going to be taking place. So actually, just as you see down here in that figure, we're going to start diminishing, right? You'll also, if these were superimposed right here with the thing, you'd also see there's a little bit of a difference in natural frequency. I'll do this, but we'll see that soon. I put another thing in here. It was like slowing down, maybe, is a thought. Slowing down of the vibration. So not only slowing down, but also the amplitude starts to down of vibration. That's what damping is and what it causes. And it makes so it makes it die away. It makes the vibration die away. What happens if it just keeps going? So the motion just keeps moving. Motion just keeps going. It keeps Energizer Bunny kind of keeps going. So if there's nothing to stop it, it'll just keep going on forever, and we know that doesn't happen. So what kinds of damping are there? Nice categories right here. Well, the main one, and I'll put a star next to it, we call it viscous damping. That's the one we most often associate with damping for vibration right here. And this is really sort of a fluid structure thing going on. Fluid structure contact, maybe say. There's fluid and structure in contact with each other, and so the viscosity of the fluid it helps to slow down the vibration, and so, like, the best example we have really that we see most often is a shock absorber. And so down here we'll see something similar to that right there. We see that we have a fluid inside this cylinder, and there's a piston, and it's got a little tiny orifice in it, and the fluid has viscosity, so it does, when we go to move this motion right there, it's got to go through this little tiny orifice, and that makes it sluggish. Also, this fluid will heat up a little bit, right? So we'll be changing that mechanical energy, which is the motion, into some thermal energy. You wouldn't really be able to, like, it'd be such a small amount of temperature rise that you wouldn't even be able to measure it. But that's the kind of idea. So that's the viscous damping that happens. Other types, we can also have friction. So we can have friction type damping, and that's really going to be like, and this is, I'll put another name for this, is also AKA Coulomb damping. Coulomb, I think I got that right. Maybe not. Coulomb damping. And this is usually going to be a solid-solid interface. Solid-solid contact. but we get the idea, right? So we get some kind of maybe a, we show like a little box happening right here, right? So the friction that's going on there is going to be a friction force involved, which is, oops, I should write equals the coefficient of friction times the normal force. And also, by the way, in a vibration thing, what's interesting is the force changes direction, obviously, if you had like a spring like this right here that's being placed onto the thing. But that would slowly reduce the vibration. There's a difference between the behavior of a friction type of damping compared to a viscous type of damping. That particularly is the viscous is a function of, as they show in this little tiny guy, it's a function of the velocity, right? So we'll write that down somewhere in there. The friction, damping friction, is going to be C times X dot, as compared to the spring, which is K times X. Or you could even think, I'm going to call it I, like the quasi-inertial force, which is going to be M X double dot. So you can see that those kind of form the basis of the equation of motion that we're about to come up with, because these are all forces and a force balance, or F equals ma, and here's the ma portion of the thing. We will be able to come up with things that are proportional to position, velocity, and acceleration, and that's the viscous one. And the friction one's a little bit different. The last one here that I'll put in there is probably other kinds. I don't know. Maybe we can imagine somewhere, but we'll call something a viscoelastic. And I don't think we do anything in this course with it, but we should know that this is like an internal to the material. And so, like, if you had like a little bouncing ball, right? How does that happen? Well, they kind of the squishy of the ball has it heats up. Or you could even have like a rubber in a tire. When we roll a car, there's some like the tire is getting squished as it's rolling down, right? But exaggerate. There's a flat spot right there. And so there's energy being absorbed and dissipated inside the tire because the air inside the tire is getting squished, but also in the rubber itself. So that's the idea in a viscoelastic type of thing. So there's some kind of like viscous things going inside the material, but there's also the elasticity, the combination to make this. I believe sometimes, check me up on this. This has the interesting name of hysteretic. I think that's the pronunciation and spelling of this viscoelastic thing. Let's see, how are we doing with time? I can't see it right here, but I'll go on to the next slide. So just some of the views of this stuff right here. So here is sort of this combination of a sine wave, and you could even tell right here. When we're going to actually explore this some more in next week, when we take a look at the log decrement. That's what we mean by here, is we're going to see how this thing decays with time. But we can see that we just superimpose this this curve, this dying curve, which is an e raised to the negative something times time, and that gets multiplied by the sines and the cosines of the thing to describe this motion. So here is our main model where we're including, and this is often called, this thing up here sometimes is represented by this symbol, and this is often called a dash pot. So getting used to those terms is a good idea. I think I want to go to another video for this, and that'll be a long video. It's an important video that describes the formulation of the equation of motion and the introduction to the solutions to it, and then we're going to explore probably in another video more details in the 3 different main cases that we have. So let's end this and discard that and put this up. And that's exactly 10 minutes. So goodbye.